Okay, good afternoon, class. Um, Mr. P here with some more workbook pages for you. Um, so, I hope everyone's doing well. Second, move my document camera out of the way. Um, so, let's see. Today was kind of exciting. I got my forge today. Um, so, I'll be posting some pictures of it on the Discord once I get it unboxed. I got it like half an hour ago. It arrived at my doorstep, so I haven't opened it yet because I was teaching. Hello, Simon. Hello, Ava. Hello, Vicky. Hello, Elena. Hello, Sebastian. I wonder if Sebastian and Elena are in the same room while they're watching the lecture, or are you each in your separate bedrooms, or what? Like what? Why don't you just watch it on the same thing? But I appreciate everyone who's watching live. It gives me good energy. All right. So let's get to the physics. So I've got, we finished up forces yesterday, and so I'm going to be moving on to work and energy. You're welcome to do any workbook problems any workbook pages that I didn't assign, if you want more practice. The other thing I wanted to say is, if you check the Discord, I posted some announcements last night. College Board is, they sent me an email, or they sent all AP teachers an email with some documents that are explaining how the AP test is going to be for you guys. So you might want to take a look at that so you know what to expect when you take any AP exams if you're taking them. Okay. All right, so this scenario, starting from rest, a 1 kilogram cart moves to the right along a horizontal surface that exerts a negligible friction while being pushed by a horizontal force F as shown. The force exerted on the cart as a function of displacement is graphed below. So force versus displacement, the area under the curve is called work, and that's energy added to an object. Claim the cart will have a change in mechanical energy of 48 joules as its displacement is changed by 12 meters. Collect evidence about the physical meaning of the area under the line on the graph that can be used to support the claim above. Write an equation including units for the area between the force line and the x-axis between 0 and 12 meters. So I'm not going to do what they said. I'm just going to show you. We can see that the width of this is 12, and the height of this is 4. 4 times 12 is 48, so it's going to be 48 joules. Explain, part B says explain how the graph above could be used to determine the final speed of the cart after 12 meters. So what I would say is the work done on the cart is converted into the cart's kinetic energy. Thus, the equation work equals 1/2 mv squared could be used to solve for v. So that's what I would do. And you actually had a test problem like that way back in the first semester. Hey Theo, Hey, Andrew. I think that's really weird that Sebastian and Elena are sitting right next to each other, but they're each logged on to their individual accounts. That's very bizarre to me. On the grid to the right, sketch a graph of the acceleration of the cart as a function of displacement from 0 to 12 meters. It's a 1 kilogram cart, and we see that the force is 4 newtons. So what that means, according to F equals ma, we know that the force was 4, and we know that the mass is 1. So that means that the acceleration is 1, or 4, excuse me, meters per second squared. An important thing there is that notice how it says that the horizontal surface exerts negligible friction. So that tells me that the 4 Newton force that was applied is the only force, and it is indeed the net force. So I can put just 4 on I don't have to do minus friction on the left-hand side. So the force was constant, so that means the acceleration is constant at 4 meters per second squared. After creating her graph of acceleration versus displacement, Angela says, oh, the slope of a velocity graph represents the acceleration. So since the acceleration is constant at 4 meters per second squared, the velocity should be aligned with a slope of 4 meters per second squared. I agree with Angela, right? I agree. I think everything she said is correct. Maybe I'm wrong. Am I missing something here? That sounds really correct to me. Sketch a graph of. Well, one thing I would say is I'm going to add the slope of a velocity time graph is acceleration. You get what I'm saying? But we want velocity as a function of. So Angela doesn't really say what is on the horizontal axis. So that's kind of the thing. So I agree with Angela, but she needed to specify that it's a velocity time graph. But we're making a graph of velocity versus displacement. See, so they're trying to mess you up there. So let's work out the algebra. So we know that work equals force times displacement. And we know that the force is constant. We also know that the work becomes kinetic energy. So on the left-hand side, I have 1/2 mv squared. Okay? So what do we know about the force? We know that the force is 4. We know that the mass is 1. So I have 1/2 times 1 times v squared equals 4 times x. So that says that v squared equals 8x, which says that v equals 8x to the 1/2 power. Okay? So notice how Angela's statement is wrong. It's not going to be a straight line. It's going to look like a square root. Okay? So we can see that at 0, the velocity is 0. If I plug in 2, I would get square root of 16, which is 4. So the velocity as a function of time is linear, but the velocity as a function of position is not linear. What if I plug in velocity equals 8, or position equals 8? Then I get 8 times 8 square root, which would just be 8. And then, yeah, so you can see the graph kind of looks like this. Kind of like that, it's bendy. The equation v squared equals v initial squared plus 2a delta x can help describe the velocity of an object with a constant acceleration as a function of position. Is this equation consistent with the graph you sketched in part E? I'm going to say an emphatic heck yes. All right, because look at v squared equals v initial squared plus 2 times the acceleration, which we said was 4, times the displacement. So that says v equals square root of 8x. So it's the exact same equation, okay? So we aced it. Okay, we got a new scenario. Let me see if I have any questions. No questions. A ball falls from rest from a height h. Consider the ball to be the system. Part A, draw a dotted circle around the system. Okay, I drew it. The dot at right represents the ball. Draw a free body diagram showing and labeling the forces exerted on the ball. Each force must be represented by a distinct arrow. So I'm going to assume that the ball has already been released because it says that it's falling. So that means that there's a downward weight force, mg. And then I'm going to assume air resistance is not negligible. So I would also have air resistance going up. Okay. On the graph below, sketch a graph of the external net external force on the ball versus height. What are units of area under the curve? So basically, when the height is big, the net external force is large. Now, why do I say that? I say that because when the height is large, the ball hasn't picked up a lot of speed yet, so the drag force is 0. So that net external force is just weight when the ball initially starts dropping. But then, as it falls, the drag force is going to basically start to cancel out the weight force. So as the height gets smaller, the net external force is going to start to go down, okay, in some manner. I didn't draw it going to 0. If the net external force went to 0, then that means it reached terminal velocity. What does the area under the curve represent? It represents the work. Okay. I think I answered the question. All right. Part D. Fill in the energy bar chart to describe the energy of the system from when the ball is dropped to just before it hits the ground. What is U sub G and U sub S? I'm not sure what they mean by that. Anyone know what that means? Gravitational potential energy, what's U sub S? I have no clue what that means. Doesn't even say what S is. That's a horrible question. All right. Well, we know we start out with a no kinetic energy, and we end up with kinetic energy. Okay? We start out with gravitational potential energy. Okay? And we end up with no gravitational potential energy. Now, the external force, I would say, is air resistance, which does negative work and reduces the energy of the object. Does mechanical energy increase, decrease, or stay the same as the ball falls from height h? I would say the mechanical energy actually decreases because since kinetic energy is dissipated and becomes heat. You know what? I think I've misinterpreted this question. Notice how it says that for this part, the I'm sorry, you guys. I totally messed this up. So notice how it says, okay, I should have cued in on this. Choosing systems. Okay? We're choosing our system to be just the ball at first. Now, a ball has kinetic energy. Okay? I need an eraser or something. Maybe I can. How do I erase what I said? Okay. So I'm just going to explain it in words. Because the system is only the ball, there's no gravitational potential energy. Because gravitational potential energy means that there are two things in the system that are attracting each other. So if I define the system to be just the ball, there is no potential energy. And what we're going to do is we're going to think about the external gravitational force as being external work. So gravity is doing positive work to speed up the object. Okay? So the external work from gravity becomes the kinetic energy of the ball. So we're basically, by making the system include only the ball, gravity becomes an external force that does work on the system, and we don't have gravitational potential energy. So that's a little bit confusing. It's not the way I learned about energy, but it's the way that the AP exam likes to talk about it. So I'm going to say that the mechanical energy increases because the kinetic energy goes from 0 to not 0. Okay? So there you have it. If the system were to include Earth how would that change the energy bar chart? So now we have no external work because gravity is now an internal force, part of the system. So now we have gravitational potential energy. We start out with no kinetic energy. I still don't know what U sub S means. Then we get kinetic energy, but we lose gravitational potential energy. Okay? So basically, the external work is not external anymore if we include the Earth in the system. If the system were to include Earth, would the mechanical energy increase, decrease, or stay the same while the ball is falling? It would stay the same if we neglect friction, if we neglect drag force. If we don't neglect drag, it goes down. Okay? All right. So I apologize for that. That's an important point for the AP exam, though. If the system is only one thing, then there's no gravitational potential energy. Okay? The gravity is considered an external force in that case. If there are two things, then gravitational potential energy can be included. All right. So I'm going to do 2 more pages here. A ball is released from rest at height h above the floor. Consider the system to be the ball and the Earth, so I can include gravitational potential energy. Air resistance can be ignored. So that means that drag force isn't removing energy from the system and dissipating it as heat. On the following axis, sketch graphs of gravitational potential energy versus distance fallen, kinetic energy versus distance fallen, and total mechanical energy versus distance fallen. So, gravitational potential energy drops linearly as the distance fallen increases. Why do I say that? Because the formula for gravitational potential energy is mgy, which is a linear function, okay, of position. The kinetic energy is going to go up, okay? Now, these lines should have opposite slopes. I tried my best to draw them with opposite slopes. I don't know if I succeeded or not. The reason that they should have opposite slopes is because if the gravitational potential energy goes down by 1 joule, the kinetic energy goes up by 1 joule, okay? Now, the total mechanical energy is remaining constant, okay? And it's equal to the value at the beginning, it's equal to the value at the end, okay? So now, notice how this first graph was versus distance fallen. But now we have versus time. So that's going to make it tricky. Well, not that tricky, but okay. So we have U equals mgy, but what is the thing that's changing in time? It's the elevation that's changing as time goes on. So I'm going to actually replace y with a kinematics equation, which is going to be y naught minus 1/2 gt squared. Okay? So notice how the as a function of time, it does not look linear. It actually looks like a quadratic that is concave down. Okay? So that means that my potential energy versus time kind of looks like this. So it's curved down. Okay. My kinetic energy is, again, it has to look like the reverse of that, because, so it's going to look like this. Okay. Because, and if I take the kinetic plus the potential and I add them up, it's always going to equal a constant. So that makes sense. All right. When the ball is halfway to the ground, is the kinetic energy more than, less than, or exactly equal to half its maximum kinetic energy? I'm going to say it's exactly 1/2. Why would I say that? I would say that, well, the total energy equals a constant. Now, what is the initial energy? The initial energy is mg h. Okay? Now, the final energy, if we've fallen halfway, it's k plus mg, and if it's fallen halfway to the ground, its height is h over 2. So k plus mgh over 2 equals mgh. So we can see that k is equal to mgh over 2. So half of the initial energy. So it has exactly half. When the ball is halfway through falling at time t equals 1/2, is the kinetic energy more than, less than, or equal to half of its maximum kinetic energy? I'm going to say it is less than. Okay. Now, why would I say that? Going back to my graph here, see how if we're at half time, so here's half time, here's where my potential energy is. Is that more than half the energy? Yes. So I have more than half potential energy and less than half kinetic energy. So I would say something like, see the graph at t equals 1/2. The potential energy is more than half the energy. Okay? So I think that's it. Those are the questions I'm doing for today. I hope that was instructive. I would say the trickiest part was definitely the defining the system. Okay, so if you're taking the AP exam, beware of that fact that if you define your system to be just a single object, then the only form of energy you have is kinetic energy. Okay? And then gravity is an external force that does work on the system and adds to its energy. If your system is two things that are attracting each other via gravity, you have kinetic and potential as part of the system's energy, and then there's no external force. All right. I hope that's clear. If you have any questions about that distinction, ask me in Discord. Also in Discord, I'll be posting pictures of my forge in about 15 or 20 minutes. So have a great afternoon, and I will talk to you tomorrow. Bye.